Hello everyone, this is section 15.3, double integrals with polar coordinates. So you might recall from Calculus 2 polar graphs, we had special types of graphs like rose curves. You might remember what they looked like, kind of like a little flower with petals, cardioids, like a heart. Spirals we could have, but all of them involved are in terms of theta. First off, recall from Calculus 2 some of the polar coordinate theory. Basically, we want to be able to go from an ordered pair of xy values in the Cartesian system to values of r in terms of r and theta. So if we look at, let's say, the Cartesian system, and for simplicity, we'll just focus on the first quadrant. Let's say we had a point here in the first quadrant, x and y. What we want to do is be able to describe that same point by traveling a distance r along a direction theta. And so to get the relationship between x, y, r, and theta, consider just dropping a perpendicular here, creating a right triangle. Okay, the horizontal leg, if this is the point x, y, to get there, we'd have to move this many units, x units in the x direction. So the horizontal leg is going to be x, and y units in the y direction, so the vertical leg is going to be y. And then the equations that we could create in terms of the conversions, let's say we're given x and y and we wanted to find r and theta, then we could state that r squared equals x squared plus y squared by the Pythagorean theorem. That will give us r if we know x and y. And then if we want to find, if we know x and y and we want to find the angle theta, then we could form a trig function in terms of x and y, and the most convenient one is to consider tangent is y over x, so tangent of theta is y over x. So those two conversion equations allow us to find r and theta when given x and y. And now if we're given, let's say, r and theta, and we want to find x and y, we'll form a trig function in terms of theta. Let's say we're going for x, in terms of theta and r. So with respect to theta, x is the adjacent, r is the hypotenuse. So we could state that the cosine theta is x over r, and then transform that, and we could multiply both sides by r. We could say x is r cosine theta. So now that allows us to find x when given r and theta. And then similarly, if we want y, knowing theta and r, trig function in terms of theta, y is opposite, r is hypotenuse, so that'd be the sine of theta, would be y over r. And then we could say that y is r sine of theta. So those are all the different conversion equations that we have. To go from polar to rectangular and vice versa. Well, here's just a little example of an integral that is typically one that we may encounter. So just for a little practice, getting warmed up. Okay, work from the inside out. So with respect to r, integrating theta is held as a constant, so cosine of theta is a constant. So we'd have the integral from 0 to pi. And integrating r squared, we get r cubed over 3, or let's say 1/3 r cubed. And again, the cosine theta tags along as a constant. This is evaluated with respect to r, so you might want to say r goes from 0 to 1 minus the sine of theta is the upper limit of integration. And then all of that's going to be evaluated with respect to theta. So then upper limit goes in, let's bring the 1/3 out in front, and the integral from 0 to pi now of the upper limit goes in, so 1 minus sine of theta goes in for r, so 1 minus sine of theta quantity cubed times cosine theta, and then it would be minus the lower limit goes in, but the lower limit is r is 0, so if we put a 0 in here for r, this all goes to 0, so no need to write it, and that's with respect to theta then. Okay, well this is actually going to require a u substitution, where we're going to choose u to be 1 minus sine of theta. Our du would be minus cosine theta d theta, and that means a negative du would be cosine theta d theta, and so that would give us 1/3 integral, I guess I'm going to say a to b, because it's not really right to say 0 to pi, of u cubed, well, negative u cubed, with respect to u, because of the fact that this was our u cubed, and then the cosine theta d theta represented the negative du. So then that gives us negative 1/3 u to the 4th over 4, evaluated from a to b, which would be negative 1/12 u to the 4th, but let's put back our u at that point. And the u was the 1 minus sine of theta. So now to the 4th, and now we could say we're evaluating from 0 to pi. And so that gives us, upper limit goes in, so negative 1/12, 1 minus sine of pi. Quantity to the 4th minus lower limit goes in, so minus 1/12 times 1 minus sine of 0, and that as a quantity to the 4th. And so at that point we get sine of pi is the sine of 180, and the sine of 180, use your calculator or the unit circle, sine of 180 is 0, so we get negative 1/12 times 1 to the 4th, and then let's make this plus 1/12, and then sine of 0 is 0, and so that gives us 1 to the 4th, and then we get negative 1/12 plus 1/12, so it turns out we actually get 0 for that. But that was just a little warm-up for what's about to come in terms of some of the types of integrals that we're going to see. Now, with regards to the integration theory, consider, let's say, maybe you have a little piece of a radius here, let's say going from 0 to pi over 2, and the area, instead of taking vertical strips like we do, we're going to take all these little rays as we sweep through that angle if we want that area. And here basically we've got the area between, let's say if this is 1, then the radius is 1, and we're going from 0, the angle theta, from 0 to pi over 2. But let's just say we have a little piece of that maybe. You can consider the whole thing, of course, but let's just say we're going to concern ourselves with a little piece of this. And get out here. And I'm going to sweep through a little angle that is of a differential d theta. So one little angular sweep. And what we're going to see is basically, let's do this. Okay. I'm going to call this distance the inner radius, r sub I, and then I want to call this distance the outer radius, r sub O. And this region here will represent the differential dr. Okay, so the difference between the outer and the inner radius will be that little width. And we've got this differential d theta, and then we've got in here, that's going to be the differential of the area. Okay, now if we spin this thing around 360 degrees, so just imagine drawing a little circle here and the outer one as well. Okay, and we'll shade in all of this outer region. Okay, so all of that outer is going to be the shaded region, including the DA piece. So the shaded area is going to be, basically it's the area of the outside circle minus the area of the inside circle. And so pi r squared is the area. So pi r sub 0 of the outer squared minus pi times the inner radius squared. But then we're going to do something with this, and you'll see why momentarily. Now factor out the pi, and so I'm left with pi times the quantity r sub outer squared minus r sub inner squared. And then, for a reason that we'll see momentarily, I'm going to factor the difference between two squares. So r sub outer plus r sub inner times r sub outer minus r sub inner. Okay? So excuse me. So that is an expression for this whole shaded area. Okay, again, the whole thing all around the outside, that little disc, if you will. Okay, and then we're going to consider setting up a proportion here. This differential dA of area is to the entire shaded area, as the differential d theta is to the entire circular sweep of the angle, which would be 2 pi. So this little piece dA is a proportion, that little piece over the whole disk thing, and then that is in proportion with the little angular sweep over the entire angular sweep, which would be 2 pi. Okay? So then at that point, we could say that the differential dA is equal to the shaded region over 2 pi times the differential d theta. And we could replace the shaded region by pi, what we found up here, r sub O plus r sub I r sub o minus r sub I all over 2 pi. So that's shaded over the 2 pi, and then times the differential d theta. But this r sub o minus r sub I, that's actually the differential dr, because we defined it here to be the outer radius minus the inner radius. So, and then we do one more thing. We're going to call r sub o minus r sub I the average. And notice that the pi's are going to cancel. So we get our average times, so that's r sub o plus r sub I over 2 times dr d theta. So this is where our average is the outer plus the inner radius divided by 2. Okay, so therefore it follows well, I'll say it down here. It follows then that the differential dA we'll just say as r dr d theta. So that was very important to prove that, because it's part of our formula for the differential of the area. That's going to be extremely important. Now, one last thing is concerning the volume. If you had two, let's say you had two curves, doesn't matter what they look like, and let me say that the outer one's going to be r equaling r sub 2 of theta, and the inner one's going to be r equaling r sub 1 of theta. Then I'm going to put my point here, and I'm going to get rid of some of this. Is what I really wanted to draw, something that looks like that. Okay, and we want the volume, or the area, if you want, this shaded region between the two values of r. Then we're going to take this theta to be equal to alpha, and this theta radial line equal to beta. And so note that just two things here. The limits of integration are from alpha to beta, and that r varies from r sub 1 of theta to r sub 2 of theta. Okay, so that leads us to the following theorem. So if the boundaries are the rays, theta equaling alpha, theta equaling beta, as we sketched here, and you got the curves R1 and R2, then the double integral over the volumes, the double integral over the region of whatever the function is. So function's up here, whatever it is, there's the region of the area, but then you got some function up, up or below the curve, that region, like rectangular regions and non-rectangular regions and so on. So you got some function of r and theta. And the dA is very important because we had proven here that the dA is r dr d theta. Okay? So that's why we took the time to show all of this, because dA equaling r dr d theta is monumental. And then you got the limits alpha to beta, and there's the inner function radius and the outer function radius. Okay? So that's the theory. And got some examples. And in the first example, I think we can get through this quickly. We want to evaluate by converting to polar coordinates. And I think we'll stop right there for this one. So we'll come back and we'll probably have a couple more parts to this lesson.